Start recording. Okie doke. So, um, I've got 4 tests submitted right now. So I need the other 6 at some point. Um, oh, I'm missing the other Caitlin. That's who's missing. Um, and there seems to be a few people that are struggling. And the only thing I can do to help out really is to offer more time. So what I'll do is like I don't want people to like turn in like a half done exam, right? That doesn't do anyone any good. So I will push the time back till midnight tonight. You can just email it to me by midnight. And if you've already turned it in and you're like, well, shit, I would like use this time to um, I would like to spend more time with my exam. I'm not going to start grading them till I have all of them. So if you want to like resubmit your exam later on today because you have more time to look at it, that is fine, but I don't see the point of having everyone like not turn in a completed exam. So I would rather just give everyone some more time and let you resubmit if you want. Uh, if you have questions, you can come by and talk to me, or well, email me and we can set up a Zoom call. Like have lab at 2, but other than that, I can. We have office hours today, so if you want to come by and ask a question, that would be perfectly fine. I'm sending out an email, so maybe if Olivia is feverishly working on her exam, she will see it and be like, "Oh, I can come to class now." Um, so yeah, trying to remember where we were at the end of last class. Does anyone remember what slide we were on? We were on 21. Of epoxidations or amino hydroxylations? So we made it to epoxidation. Okay, cool. Okay, so let's share some screens, and of course I have to do it in this weird way because I can't ever like get it to work the other way. Um, so dihydroxylation. So I kind of did these in like reverse chronological order almost. So dihydroxylations were the first of these to be discovered and published. So these use as a ligand diethyl tartrate. So you may remember the story I told in Organic 1 about tartaric acid uh, making enantiomers. And so this is that acid. And so you can you make the ester and then use the chirality from these 2 alcohols as how you induce your chirality. So you use this titanium metal to do the epoxidation. And if you look at the olefin, right, the D enantiomer comes from the top and the L enantiomer comes from the bottom. These have to be done as allylic alcohols. Where the dihydroxylation, you don't need like any kind of functional groups around. This you need to have an alcohol on the allylic carbon to kind of direct where the metal is going to go. So again, I'm not going to ask you to predict, if you're going to make which enantiomer you're going to make, just to know that you can make one of the enantiomers, right? You just have to pick the right ligand is enough for me. So you have the ligand, you have the titanium tetraisopropoxy, and then tert-butyl hydrogen peroxide, which is this here. So you're just replacing one of the hydrogens of hydrogen peroxide with a tert-butyl group. And that is your terminal oxidant. So that is what's actually oxidizing everything. So a couple examples. You have this allylic alcohol here, where you're able to react here and here. And now notice this double bond in the middle doesn't epoxidize because it's not near an allylic alcohol. So it can't epoxidize. It has to be by an allylic alcohol. Right. And so you're able to do both of these simultaneously. Fun fact, T.R. Hoy, I went to grad school with his son. So that's Tom Hoy. He's up in Minnesota. I went to grad school with his son. Small world. I was going to start singing It's a Small, Small World, but then I realized no one even wants that at 9:30 in the morning. Can't handle that. Here again, another simple example where you epoxidize this alcohol. You notice all of these have really, really, really good enantiomeric excesses. Like 99% is effectively only one isomer. It's 99.5 to 0.5. It's effectively you just made one enantiomer. And then here's some examples here's an example on a bigger molecule, right? If I can find it, there it is. So this double bond right here reacts over this one. And if you look at it, this double bond's a little bit easier to get to, right? They're both allylic double bonds, or they both are allylic alcohols. But this one, you have a CH2 here, and this one you have a branching. So the catalyst is going to react with this double bond a little bit faster than this one, which gives us this product for this epoxide here. And then this one I thought was just kind of a neat example where they're able to epoxidize the double bond of an indole, and it makes a ring. So the way this works, right, not so much the epoxidation, but the actual ring closure, right? So if you have your indole, we're just going to put an R group here, and you do your epoxidation. Put another R group here, so I have to do the whole thing out. No, I need the whole thing, sorry. 1, 2, OH, right? 2, it's 2. Right? We're going to make an epoxide. Now the lone pair on my nitrogen can push that epoxide open, right? Because the epoxide is strained and we want to relieve that strain, so we're able to push open that epoxide. Now I have 1, 2, 3, 4, 5. Right now I have a carbon that is electrophilic. So my lone pairs on my nitrogen, on my oxygen, can then add to that carbon, move electrons over, and then we just lose that proton to solvent or water that's in the reaction or generated in the reaction. So we can take this and just have some base. Right, we could say water, come grab that proton, and make the product. Right, so we make the epoxide there, but we don't really care about the epoxide. The epoxide is just there to, right, give you a reactive intermediate, a reactive compound, and set this chiral center here. Right, it sets that chiral center, and then that then sets this chiral center. So the epoxidation just makes a chiral alcohol in the end. Right, you make the you make the epoxide here, but you don't want the epoxide. You want the epoxide as a reactive intermediate. You set this chiral center when you make the epoxide, and that chiral center stays set throughout the rest of the reaction and dictates how the cyclization is going to happen. So if your OH is up, right, go over. So if your OH for your epoxide is up, if your OH is up, that puts the alcohol chain down, which then means it has to come from the bottom, which then means when you cyclize, you're going to end up with basically your oxygen down, your hydrogen up, which is what you see in the product. I'm drawing more wedges and dashes than I need to, but just to really drive home what side everything's on. Yeah, I'm all by myself today. No one came. So like, I don't want to see him after that test. It's awful. So the cool thing or the good thing about a sharpless dihydroxylation is that they are usually catalytic, so you don't have to use a full equivalent of the titanium or the ligand, right? They just need a little bit and they work, right? And the ligand, diethyl tartrate, is super cheap, super available. It's not hard to come by, right? So that's why catalytic reactions are so good, is that they don't require a lot of any of the components. Now, there are other versions of like these asymmetric reactions that use like chiral reagents, where you have to have a full equivalent or more of the chiral reagent, and that just makes them a little more expensive and a little more difficult. Oh, before we go, so Sharpless, K Barry Sharpless, he's at Scripps La Jolla, which is like paradise. Dr. Lee and Perez Alvarado both went there for their postdocs. But Sharpless, rumor has it, is blind in one eye because he didn't wear his goggles and a student was heating an NMR tube, and the NMR tube shot hot chloroform into his ungoggled eye. So even if you have a Nobel Prize, you still have to wear goggles. So he can only see his Nobel Prize out of one eye. Just must be sad. Right. So you have She epoxidations, So the She epoxidation is not catalytic. You have to make a full equivalent of this big sugar catalyst. Well, no, I guess it is catalytic. Never mind, I'm dumb. Don't listen to me. Well, no, listen to me. Listen to me. I'm sorry, it's early. So you make this big sugar reagent. So this actually takes a little bit more work than just like taking tartaric acid and like treating it with ethanol. But the catalytic part, the oxidant that's actually doing stuff is this is oxone, is KHSO5, or hydrogen peroxide. And these react with the ketone and make it so the ketone can transfer an oxygen to the double bond. So there are a bunch of different versions of this catalyst based on different sugars. I think this is the fructose-derived one, but I barely got a B in biochem, so I don't know. It's a sugar. All the people in biochem should be like right on this. You should be like, oh, that's totally blah 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 blah. Right. So you basically just protect the two alcohols or two of the alcohols on the sugar, and then oxidize the last one, the ketone. So not only do you have to like have the conditions figured out, but you have to know which sugar you need to use for your epoxidation. Now the upside is I don't need to have an allylic alcohol. All right. The downside is these really only work on tri-substituted double bonds or di-substituted double bonds, but c'est la vie. So the way this works is it's similar to an epoxidation with DMDO. So DMDO is dimethyl dioxirane. So you take acetone and you oxidize it with oxone, and you make this three-membered ring with two oxygens in it. It's not particularly happy and is able to transfer one of its oxygens to a double bond to make an epoxide. All right. So the She epoxidation catalyst does the same thing, where this ketone gets oxidized with oxone and makes this three-membered ring. Now this three-membered ring has chiral centers around it, here and here, and so it has a chiral environment. So the double bond kind of has to approach one face of that six-membered ring over the other. So like if you were to look at this catalyst, right, you could probably guess that these oxygens, this ring right here, is going to block the bottom face. Same with this. So your double bond would come from the top, and then it kind of has to orient itself in a certain way as to not bang into the rest of the molecule, and that's how we get our chirality. Is we kind of dictate which side of the catalyst it approaches, and then the rest of the shape of the catalyst determines how the double bond is going to interact with the catalyst. Again, it's super hard to be able to like predict what's going to be wet. So this is one of these are these things that I want you to know they exist, right? So, you know, if you had a situation where, say, you had a double bond and you know you had to make a chiral epoxide, right? If you needed to say what the reagent was, well, it needs to be a chiral epoxide and it's not an allylic alcohol. The way you know how to do that would be a She epoxidation, right? And you could like write one of the catalysts, but and then the reagent, right? But if that's not like the exact right catalyst, that's fine, right? You would have to, for whatever the example was, experiment and figure out exactly which sugar was the right sugar to use for that reaction. And so that's not something that you guys can like easily just know from first principles. That's something we'd have to experiment on. So it'd be more like, yeah, I know that the way to do this is a She epoxidation, and I would use reagents that look like this, but I might not be picking the absolute best reagent, and that's fine. We just need to know. I just want to know that you know that this is what I would be trying to you'd be trying to do, right? So these work pretty well in kind of unfunctionalized, or not unfunctionalized. Like you don't need to have a specific functional group near your epoxide, near your double bond that you want to make your epoxide. Just have a double bond and it will work. So back to the slides. So here we've got double bonds. So this is the double bond that reacts. So you see this double bond is by an aromatic ring. This double bond is conjugated to a ketone, right? So double bonds that are conjugated to ketones are less reactive than double bonds in these kind of reactions, are less reactive than double bonds that aren't conjugated, right? Which makes sense because on some level, the way this works is that your pi bond attacks your reagent. So you have, right, you've got a double bond, and then we'll just use DMDO, right? Your double bond attacks the oxygen, breaks that bond. Well, here, I'll do it this way. Electrons come down, and then these electrons come over and add, right? But the first step is adding your is having your pi bond attack the DMDO or the DMDO derivative, right, to make your epoxide plus regenerate your ketone. And so if you have a carbonyl group on your attached to your double bond, right, through resonance, there are less electrons in that double bond than there would be otherwise, right? Because they're getting pulled towards the oxygen. So there are less electrons in this double bond, right? Which means it's harder for it to go add to something. So in this example, right, I've got two double bonds, one that is conjugated to a double bond, to a carbonyl, and one that isn't. And so the one that's conjugated to the carbonyl is less reactive. So the She epoxidation reacts with this double bond first. Right? Now there is a chiral center here, and you can think of any asymmetric reaction is either being matched or mismatched, meaning that your reagent can be matched to the chiral center that the substrate wants to give you. So if we like minimized A13 strain, yada yada yada, we could see how this worked, right? And so let's say it wants to come from the top anyway, right? But maybe if you don't use the chiral reagent, you get like a 1.5 to 1 selectivity, which isn't really good. But then you use your chiral reagent that is reinforcing the stereochemistry that the substrate wants to give you, and that will help make your enantiomeric excess, or in this case, diastereomeric ratio better, right? So you can have your catalyst matched up with what your substrate wants to give you, or they can be mismatched, where you're asking your catalyst to overrule the selectivity that your molecule is already prone to give you. And sometimes that works fine, or you can say like, well, the molecule wants to make the S stereocenter, but I need R, and I can get my reagent to overrule it, and I can get enough R that I can go forward. In this case, I think they're matched, where this wants to put the epoxide on the top face, and this methyl group also wants it to come from the top face. So I think all in all, these are a matched case. Here, they have two double bonds that are conjugate, that are beside an aromatic ring. We only react with one of them, and that's because cyclopropanes are weird. So, as a general rule, right, if you have a cyclopropane, I'll make it secondary, right? So having a carbocation beside cyclopropane, that carbocation is a little bit more stable than if it was just a regular, just boring secondary carbocation with no cyclopropane. Now, yes, you're thinking, I remember in organic one, these rearrange, and they do. But it's easier to make this carbocation than it is to make than this carbocation. And that's because, remember, cyclopropanes have Walsh bonds. They have those orbitals that kind of bend out. Those orbitals kind of interact with the pi bond, with the carbocation, and make it more stable. So when you have a choice between reacting with a, no oxygen, reacting with this versus this, if I don't make a full carbocation, the carbon beside the cyclopropane better supports positive charge. So it doesn't mind electrons leaving to go add to something, because as that positive charge starts to build up, it's more stable because of the interaction between the bonds that make the cyclopropane and the carbon that's becoming positive. So in the example, right, I have two double bonds, right? And I have two things working in my favor. This is a mono-substituted double bond. This is a tri-substituted double bond. If I start to put a positive charge here, the cyclopropane helps out and helps stabilize it. If I start to put the positive charge here, that's a tertiary carbon. And right, a tertiary carbon can better support having positive charge. So all in all, the fact that electrons have to leave this pi bond is supported by the fact that there's a cyclopropane here. So this reacts before this. You make this cyclopropane, this weird spirocyclic structure, and then one of these two bonds, this one or this one, will shift and open the epoxide to give you the ketone. So, go over. If you get to this guy, I'm gonna draw it. you can think about this shifting here, right? 1, 2, 3, 4, pushing electrons up onto the oxygen, right? So the way I have it drawn, 1, 2, 3, 4, 1, 2, 3, 4. My oxygen is on carbon 3, right? Because I broke the bond between the oxygen and carbon 4. I broke the bond, this bond right here, between carbon 1 and carbon 3. So carbon 3 gets a positive charge. The oxygen has a negative charge because it got electrons from the bond it shared with carbon 4, right? And then this is just a resonance structure of a ketone. So this is kind of the second time we've seen that we've used the inherent strain of an epoxide to after we make it to then do another reaction. So those are all adding oxygen. So we've added a bunch of oxygens, we've added a couple of nitrogens. There are some other reactions, some of which might be helpful for installing the remote stereo center, like making the chiral methyl in your molecule of the semester project. And the one that I think is most useful will be an asymmetric hydrogenation. So as the Naiori hydrogenation, and you use ruthenium and a chiral ligand to reduce double bonds. The chiral ligand is normally BiNAP, and I'm going to show you BiNAP here in a second, so don't you worry. Okay? And this hydrogenation reduces a lot of different things. It reduces alkenes, which is the examples I'm going to show, but you can also use it to reduce ketones to alcohols and introduce chiral alcohols this way. You can reduce imines to make chiral amines. The thing that comes through is that you need some sort of coordinating group to help direct that the hydrogenation. So you need some way to direct that your catalyst, but it doesn't have to necessarily be allylic. It could be homoallylic. So the alcohol or the amine that's directing the catalyst can be further away from the double bond. So I wanted to talk real quick because I want to show you BiNAP, but BiNAP is chiral in a weird way, and I want to talk about it for a second. So we're going to talk about stuff that's axially chiral. So things that don't have a chiral center, don't have a chiral carbon, but are still chiral. So we in Organic 1 kind of fell into the concept of you need a chiral center to make a molecule chiral. But then that gets broken when you have a meso compound, right? Because the meso compounds have a plane of symmetry. They stop being non-superimposable mirror images, right? And that's really deep down what being chiral is all about, is when you have enantiomers, the molecules are non-superimposable mirror images. And it doesn't matter how you get to that non-superimposable mirror image part, it just matters that is the case. So a lot of times using a chiral carbon gets you to your non-superimposable mirror image the fastest, right? So, but there are other ways you can get that as well. And one is by naphthyl derivatives. So I'll show you in a second, but by naphthyl is you have two naphthalines. This is by naphthyl. And because of how big these groups are, here and here, the rotation around this bond is pretty slow, which means you can separate out the molecules that have the groups kind of arranged differently around that single bond. So you can have the back towards you of this one and the front towards you of this one. Right? Or so basically what happens is here are your two binaptals. You can have them like this, where the bottom one is sticking out towards you, and the back one, the front part is toward you, and the top is away from you. Or they can switch, where now this is toward the top's towards you and the back's away, and the bottom one's the main part of it's pointing away from you. And because those are big, that rotation to go from here to here is slow. So at like 50 degrees, I think it takes like an hour or something, the half-life to go from this to this. And as soon as you start putting groups here at this position, that half-life goes up to the point where you can separate this isomer from this isomer, and they won't interconvert at normal reaction condition temperatures. So upwards of a couple hundred degrees, they won't interconvert. Right? They're just so big that as they go to turn, they just bang into each other, and they won't go past. So those are binaptal derivatives. And then the other version of this is allenes. Right, so instead of having a point of chirality, these have an axis of chirality. So this is the example I have drawn, I do believe. And it's close enough to it. Right, this verse this, right? So if you remember, I don't remember, allenes, the way an allene works is you've got your central carbon, right? And you've got one set of double bonds that is like this, and the other set is like this. They're turned 90 degrees, right? So that center carbon is making a bond that is in the plane of the page, right? So the in the plane, right? So that's in the plane of your page or your screen. And then the other side is perpendicular, like this, where in this case the OH is sticking out and the bromine is sticking back, right? These can't rotate or anything. So what ends up happening is these two compounds are enantiomers. They are non-superimposable mirror images, right? If I try to slide these on top of each other, everything that's in plane lines up, but the OH and the bromine don't, right? So these are enantiomers even though they don't have a chiral carbon. They don't have a carbon that's bonded to 4 unique groups. So the kind of the go-to thing that you see the most for axial chiral stuff, like I said, is binapthol, right? So this right here is binap. So the nap is for the diphenylphosphoryl here and here, right? So BINA is for binapthol, and then the P is for the phosphorus here, right? And you have the group that is back. This group is forward towards you. This side is forward towards you. Then they change, and they're non-superimposable mirror images, right? You can't slide them on top of each other and have everything match up. So they're enantiomers. Now, I will be perfectly honest with you. I tried really hard to read up on how you determine R and S, like how you determine it from first principles, and couldn't figure it out. But I know the trick. So if you have a binap, right? This is S, and you can tell it's S because the wedges make an S. Oh my God, no. No, I'm so bad at my job. There you go. Sorry. I thought I changed it. Let's go back. So here's your wedge. Here's your binapthol. And I'll put my little phosphoruses on here. PH2, PPH2, right? And this the wedges make an S. And then if you have the other enantiomer, it's a little bit more of a stretch, but they kind of make an R, right? So that one is here. Right, right here you kind of make an R. The S is way easier to see, but that's the trick. I was reading up on it, and I was like, I don't understand this well enough to tell anyone, so we'll just do the trick. But this ligand, the binap ligand with the phosphorus on it, this is the ligand that gets used for this Nenni hydrogenation. So, right, you've got this double bond here, and you have this ester, which is kind of the coordinating group. You add binap with ruthenium. And the thing about these is it takes a really large amount of hydrogen at a high pressure. So this is at 100 atmospheres. So you have to do this at 100 times atmospheric pressure to kind of force these hydrogens onto this double bond. But it works, and you get a 95% yield and 85% EE, which is pretty reasonable. Right? There's no other chirality in this molecule. This is all just from this catalyst. Right? Here, there is some chirality in the molecule elsewhere, but this, did I not actually do it? Oh, I didn't actually do it. Sorry. This should be a wedge or a dash. I'm sorry. So bad at this job. Let's fix this real quick. Okay, sure. And now talk amongst yourselves about how bad I am. Let me fix this real quick. I swear I kind of proofread these. Kind of. But I'll fix it real quick. Okay, we fixed it. It's better now. No, I don't want design ideas. PowerPoint. Okay. As we were. Share that. Okay. There we go. We actually installed our stereo center. Right. The EE is not great, but it's better than nothing. So all of these go away, or all of these stay, but they don't have any influence on how this stereo center gets installed. So if you just have a double bond that may or may not have some functional group around it, like an alcohol, right? You can use this to install stereochemistry at that carbon. So, if you just have this like methyl group and you can't figure out how you can make it chiral, you could just use an asymmetric hydrogenation as kind of as a way to do that relatively easily. So these last two are not introducing oxygens. They are introducing cyclopropanes. And I'm going to talk about two different ways to do cycloproponations. The first is a Simmons-Smith cyclopropanation. So, oops. So Simmons-Smith, you have a double bond. And the way that it gets used the most is the Furukawa modification, which is you take diiodomethane and you treat it with zinc, diethyl zinc. Let me write it actually the right way. Diethyl zinc. And that will just take a double bond and make an not an epoxide, gosh, make a cyclopropane. Good job, me. There you go. Make a cyclopropane. This is Simmons-Smith. The actual Simmons-Smith is slightly different, but the way everyone does a Simmons-Smith cyclopropanation is this way, or almost everyone. And you end up that your diiodomethane reacts with your diethyl zinc, and you make ethyl zinc CHI. And so this kind of behaves almost like a carbene. So a carbene, I should probably define. It's a carbon with an empty p orbital and a lone pair. So it's kind of like you have a carbocation with a carbanion on the same carbon. Okay. So what this means is that this carbon can be added to while also being able to add to something. So it's both an electrophile and a nucleophile. right? So you have a situation where a carbene is, you've got an empty p orbital that gives you a positive charge. Plus you have a lone pair, then you have your two groups, right? And if you look at this, ethyl, zinc, right? You can say on a carbon metal bond, right? The metal is plus, the carbon is minus, right? But a carbon iodide bond, right? You can think about what happens if the iodide leaves. It leaves as I minus and leaves the carbon with a positive charge, right? So you can think about this as almost being, well, this is kind of minus and this is kind of plus. So my carbon has carbanion characteristics and carbocation characteristics. It can be added to, or it can add to something. So like in a Simmons-Smith cyclopropanation, you end up with your double bond and you have your CH2 with your I and your zinc, and you kind of have your pi bond adds to the carbon to knock off the iodide, and at the same time, these electrons here are able to add back to the carbon of your double bond to give you your cyclopropane, and you make ethyl zinc iodide. Right. So the carbon acts as both a nucleophile and an electrophile. No, what did you do? Sorry. Resume share. Did that fix it? That fixed it. Okay, good. I could just look behind me and see what screen is being projected because that's the one you guys can see. So this is just a way that you can set up a carbon that both can be added to and add to something. Yes. Okay. Cool. We will new share now. In a normal sense, the Simmons-Smith cyclopropanation isn't asymmetric, right? You can get chirality from stereocenters that are already in the molecule, but you can't. But it's not an asymmetric reaction. But there is a variant where you use a chiral ligand and you're able to get stereochemistry that way. All right. So here, right, I have a chiral center here, right? This methyl group is down, which means the hydrogen is up. And then over here, so this dot right here is showing that a hydrogen is pointing out at you. So that hydrogen is up. So right around this double bond, I have hydrogens on the top face of the molecule. And then I have a methyl group, and then this part of the ring right here is down. So the open face, the side of the molecule that's easiest to get to, is the top face, the side that has two hydrogens. So the cyclopropane that you add is added from the top face. Right? So here we're using the stereochemistry already inherent in the molecule to direct where the cyclopropane is going to come from. Now, the asymmetric version of this is the Charette variant, where they use this chiral ligand. So this looks a lot like tartaric acid, because it is a tartaric acid derivative, but it's an amide. and then it's bonded to this boron. And if you have an allylic alcohol, right here, you can do your cyclopropanations in really good EE. So this was, this would have been 90% EE. You have a 95 to 5 DR. So you're making essentially only one isomer of the cyclopropane. Now, I was trying to find more examples of the asymmetric cyclopropanations, and what I stumbled upon was this synthesis of apotholone B analogs. So apotholone B is actually clinically used in the treatment of breast cancer. I forget what the actual name is of it, right? But from this paper, 2011, they were saying that the cyclopropane has been shown to be more active than the epoxide, and that the cyclopropane, I should say should, not use provide, should provide greater metabolic stability, which makes sense, right? Epoxides are pretty easy to open, right? We went through a whole bunch of reactions in Organic 2 that showed how we could open epoxides, right? You could open them under basic conditions. You could open them under acidic conditions. And so removing that epoxide removes a place that the molecule can be metabolized and can be reacted with. And so they wanted to see if they could install this this cyclopropane asymmetrically. And then also they wanted to change this heteroaromatic group, right? So they wanted, the last thing that they did was to introduce this ring so they could see hey, what happens if I start to change this ring? How does that impact the biological activity? Now, what we can do is we can call it here, and then we'll walk through this synthesis on Tuesday, and just one, it shows the cyclopropionation, but two, it goes through a lot of reagents that you guys know that you've learned from this semester, and I just thought it would be interesting to go through and look at how reactions that you have learned actually get used in practice. So we have but I'm going to make you actually think. So we're going to walk through and fill all these in, but all of these reactions. And I'm going to also use it as a chance to introduce two other reactions that you don't know and walk through the mechanism. But we'll call it here because I think I've stuffed your heads full of enough stuff. And an hour is enough time with me, I think. And this way we'll actually get all the way through it on Tuesday. It's supposed to partway through. So if you haven't turned in your exam, I'm just give you to midnight. If you have turned in your exam and you're oh, I want to look back over it and make changes, that is absolutely fine. I'm not going to look at them. So if you resubmit later on in the day, I will use that later submission. I think that's only fair. But yeah, if you have some questions, feel free to email me or something. We can talk through stuff. I can't be, too useful, but I can, I might be able to offer you some help if you're confused, because my goal is not to have you guys freak out. So with that, if no one has any questions, and you guys have been super quiet, so I'm assuming you don't have any questions, or you just gave up. Please don't have given up. We will do this all again on Tuesday. So we'll walk through the synthesis on Tuesday, and then I'll get up, probably add some stuff to it, but I'll get up the next stuff, which is carbonyl additions. like the predicting stereochemistry on carbonyl additions will be what we do next. So with that, I will see you guys on Tuesday. Sure, no problem. Yes, ma'am. Yeah, I'll try to throw it up. Like I don't really edit these, so I will throw it up like here in a sec. Um, do you need time to work on your exam?